So moving on to the second part of chi-square tests, and we are going to now look at how to analyze two different counts and test for homogeneity. So if we're comparing observed distributions, a test comparing the distribution of counts for two or more groups on the same categorical variable is called a chi-square test of homogeneity. A test of homogeneity is actually the generalization of a two proportion z-test. If you think back to when we talked about the null hypothesis to a two prop z-test, what we were saying is the difference in two proportions was equal to zero, or that they were equal. The calculation of a statistic for the chi-squared homogeneity are identical to the chi-square test for goodness of fit, which is pretty nice. So we don't have to add any new thing to invoke that goodness of fit test, but now we're going to be comparing two different counts. So the difference comes in how the data are presented. In the chi-squared goodness of fit, we are comparing a distribution of the levels of a single variable from a single sample. Single variable, single sample. And we're looking at that to a theoretical distribution of that variable. For a chi-squared test for homogeneity, we're comparing a distribution of categories of a variable from two or more randomly selected samples. And we're trying to determine if that distribution is consistent between those same categories of the variable across a second variable. Note, there's no model here. So do these samples come from the same sample population distribution? Since there's no hypothesized model, the expected counts must come directly from the data, and thus we have a different degrees of freedom. For the chi-squared test of homogeneity, the data will look familiar. If you remember way back to two-way tables when we talked about them in chapter 3, we used these to determine the independence of two variables. You'll recognize this data distribution as a contingency table. So last time we saw this was when we were looking at Titanic information. How many people survived from first class, second class, third class on the Titanic versus how many people who died. And we were wondering, are these distributions equivalent? The question we were asking, is the distribution of class the same across levels of the variable survival? In other words, are the ratios of alive to dead the same for all levels of class? And we did that by looking at bar charts, and then we did contingency tables, and we did stacked bar graphs, all things that you should remember doing. And if you recall, it is obvious that in this particular case, the answer was no. The chi-squared homogeneity test is how we will quantify that result. So before, we didn't have the techniques to actually say for sure why these weren't the same, but now we do, and that's where this chi-squared test comes in. Just like we always do when we're ever looking at tests, the assumptions and conditions have to be verified. So with the assumptions and conditions for the chi-squared homogeneity test, they're the same as for a chi-squared goodness of fit test, which is great. So we should celebrate that. So we look at the counted data condition, so all of our data must be counts. The randomization and 10% condition is actually a little bit different. If you don't care to generalize here, we don't have to check these. But if we do intend to generalize to a larger population, then you must check these conditions. Lastly, with our expected cell frequency condition, the expected count in each cell must be at least 5. And that's super important to check. Don't just jump straight into the test. Make sure you check this. What is different is how we find the expected values and the degrees of freedom. That's what separates the chi-squared homogeneity test largely from the assumptions and conditions that we do for the goodness of fit test. So with our calculations, in order to find the expected counts, we use the distribution of the marginal distribution to find the appropriate expected value for each conditional distribution. So we're looking at the edges of our table to then calculate the expected value for each cell. Or to put it in very calculator ways. To find the expected values, we must multiply the row total by the column total and then divide by the grand total. Please make note of this formula. We have the row total times the column total divided by all total will give you the expected value for each given cell. And if you notice this IJ notation, that's for rows by columns. And this means we're going to look at matrices, which you've seen in some previous math classes. So these values come from the marginal distributions. And we will go through a couple examples to make sure you guys understand this clearly. Once we calculated the chi-square statistic, as we did for goodness of fit, what we do is we sum up the cells from all of the components. So the component piece would be the observed value minus the expected value squared divided by the expected value. In this situation, we have R rows and C columns. And to find the degrees of freedom, we do R minus 1 times C minus 1. We'll need the degrees of freedom to find the p-value for the chi-squared statistic, because note, the chi-squared distribution is a family of distributions. So the degrees of freedom is what pins down which distribution we're using. That's why it's so important to find the degrees of freedom. So let's look at an example. Medical researchers enlisted 90 subjects for an experiment comparing treatments for depression. Subjects were randomly divided into 3 groups and given pills to take a period of 3 months. Unknown to them, one group received a placebo, the second group the natural remedy St. John's wort, and a third group the prescription drug Posrex. After 6 months, psychologists and physicians, who didn't know which treatment each person had received, so this was a double-blind experiment, evaluated the subjects to see if their depression had returned. As you can see from the table, we have a placebo, St. John's wort, and Posrex. What we want to determine is, with our null hypothesis, is that the distribution rate of return the same for all 3 treatments, with all our alternative hypothesis being the distribution for rate of return is not the same for all 3 treatments. And notice the numbers, while it be 30 in each category, we don't get the same values in each. So how do we compare these? And that's what a chi-squared homogeneity test does for us. So before you jump to the test, we have to make sure that we check our assumptions and condition. These are all counts and of categorical data. The subjects were definitely randomly assigned to treatments. The counts in the cells are independent. No one received more than 1 treatment, so that's confirmed. 90 subjects is definitely less than 10% of the population of people suffering from depression. But, now we run into issue we need to resolve. How do we find the expected counts given this chart? So let's find the expected values. So first we need the marginal distribution. The margins, if we want to tally these up, are our totals. So 24 plus 6 is 30, 22 plus 8 is 30, and 14 plus 16 is 30, giving us a grand total of 90. If we total up the row, if we do 24 plus 22 plus 14, we get 60. And if we do 6 plus 8 plus 16, we get 30. And 60 plus 30, again, is 90. Now, in this chart, what we need to look at is how can we calculate the expected values. So I'll give you one of 3 ways. And if you also notice, I'm drawing in a diagonal through each one of those cells, and that shows us how we divide up a 2-way table to show both the observed value and then the expected value. So one way to think about it is, since there are 30 out of 90 of the subjects who got the placebo, we should expect 1/3 of the people of the 60 with recurrent depression to have gotten that placebo. So if we do 1/3 of 60, we get 20. Okay, so that was looking at column and then using that to calculate row. Or we could say 60 out of the 90 that had depression returned is 2/3. So we'd expect that also to be true for the placebo. So we should have 2/3 or 20 out of 30 to receive the placebo. So that's way 2. Or the mindless way that we explained before, you do row total 60 times column total 30 divided by the grand total 90, and that gives us 20. And if you notice that the column totals are the same for each, so we would have 20, 20, 20 for our expected values for depression returned, and we have 10, 10, and 10 because that's 30 out of 90 or 1/3 for each of those groups. So now that we have the expected value and we've explained out how we can calculate that, now we need to do the thing that we did before. We need to compute the residuals. We need to square the residuals. We'll compute the components and then find the sum of the components. So our residual is observed minus expected. We square that and then we divide it by the expected value. If you can show me one or two of these calculations, then let the calculator do the rest of the work for you. So as been the case in the past, I do not need to see the entire calculation, but you do need to show me something that's not just what the calculator did for you. So show 2 or 3 of the components so I know that you know how the calculation is done. That's the important piece. So show me a couple and then we can move on. Next, we need to find the degrees of freedom. So we have 2 rows, so 2 minus 1, and we have 3 columns. Columns are vertical. So 3 minus 1 is 2. So 2 minus 1 times 3 minus 1 gives us 2 degrees of freedom. Then we jump to our calculator. We just want to run a chi-squared CDF. We have our chi-squared value of 8.4. We have our degrees of freedom. So we hit Menu, 6 for statistics. We're going to distributions, and we're going to do a chi-squared CDF. We're going to sum everything up. Our lower bound is our chi-squared sum. Our upper bound is some large value. Let's just say 999. The degrees of freedom is 2. And we get a p-value of 0.014. And because the p-value of 0.015, let's call it, is less than our baseline alpha level or significance level of 0.05, we reject the null hypothesis and we conclude there is sufficient evidence that the tested treatments are not all equally effective in preventing the recurrence of depression. Now you may be asking, Mr. Swenson, there's got to be an easier way. And there is. So you need to show me some of the work to make sure that you know what you're doing. But let's look again at our calculator. And how can we store a two-way table in our calculator? What we're going to do is use the matrices. So the button right next to the number 9 on your calculator, and then we're going to choose this last one. Here we have 2 rows and 3 columns. So we have a 2 by 3 in this case. And what we're going to do is we're going to enter each one of our cell datas. So we have 24 placebo, 22 St. John, 14 Posrex, and then no signs of depression were 6, 8, and 14. Sorry, 16. From there, right above var is STO in blue. So if I hit Control and var, I get this little arrow, and I'm going to need to name what variable this is associated. So I pick one of the letters on the calculator, and I say store that as A. And it's important that you store it as A. And if you want, you can test. You just type the letter A, and it returns our table. So what we now do, once we have our data stored in a matrix, I will go to Menu, 6 for statistics, and we're going to go down to 7 for tests. And now we want to do a two-way test, chi-squared two-way test. If I type A in for our observed matrix, and I hit OK, you can see we get our chi-squared statistic of 8.4, our p-value, again, of 0.015, our degrees of freedom of 2, and we also get our expected matrix as well as our component matrix. And just like before, if you want to have access to either of these matrices, you're going to need to hit the variable button. And from there, if you click stat matrix, I'm just going to, for our sake, store that as matrix B. And as you can see, once I hit enter, that's our matrix. If we wanted to see each of the components, for example, if you needed to show me some work, again, we could hit variables and we can go stat comp matrix. And this gives us the components for each one of the cells that we ended up adding together. The calculator will find the expected values and enter them into a matrix, which is pretty nice. So the last thing that you need to do is make a decision when we're doing a hypothesis test. So obviously, if our alpha level or significance level is 0.05, our p-value is definitely lower, so we reject the null hypothesis. My advice to you all, you should do the test on the calculator first, after you've checked your assumptions and conditions. All the values you need to complete the problem will be available to you. So once you have stated your null hypothesis, your alternate hypothesis, checked your assumption and conditions, then use the calculator and then write down the rest of your steps. Last bit, when we reject the null hypothesis, it is always a good idea to examine the residuals. For chi-square tests, we want to work with standardized residuals. And this might sound familiar to some of you, and maybe you were asking this before. Mr. Swenson, when you were saying to look at which component had the most influence, how did you know one was not being swayed by the count? And you're right, this is why we standardize things. So as we want to compare residuals from cells that may have very different counts, and it's especially important if we want to compare the counts in a cell that has a small count. So to standardize a cell's residual, all we do is just divide the observed value minus expected, divide it by the square root of the expected value. So the standardized residuals are the square roots of the components we calculated for each cell, with a plus or minus sign indicating that the observed value is greater or less than expected. The standardized residuals provide a chance to consider the underlying patterns, the way in which a distribution might not match the hypothesized, what we hypothesized to be true. And if you're thinking in terms of standardization, that would be our standard normal model. So if we're looking at these standardized residuals, then anything over 2 would be pretty significant. So looking back at our data, and if you know anything about matrices, we have our previous value, A, and then I stored our expected values in B. And if I do A minus B, I get at least the observed minus the expected or the residual values for each. Unfortunately, because of properties of matrices, you cannot multiply that by a variable. And since they're not consistent, you're going to have to find these each by hand. So if you wanted to find the standardized residual value for the placebo of depression returned, which if you look at the table I have in the notes, it's 0.8944. What you would have to do is we'll take the first row and first column number, and we'll divide that by the square root of 20. Why 20? Because that is the expected value for the first cell. It's important that you keep track of both your residuals as well as your expected values. So I hope that you guys write these down. And then once you have one, what you can simply do is scroll up, change a value. So this time it's 2. It's the same expected value for the first row. So I hit enter, and this is how, back on the notes, you can see that we get these standardized residuals. So the one that seems to be standing out the most here is the POSREX that returned no signs of depression. And it appears that people who take the prescription drug are more likely to remain free of the disease than those who took a placebo or the natural remedy St. John's wort. And that's the power of being able to do a chi-squared two-way test. We have one more test to cover, and that's to study independence, or to test independence, and then we're done with chapter 26.